Hey, hi, good morning, everyone. Good morning, friends. Welcome back to our session on artificial neural networks. So, we'll quickly recap what we have covered in the previous session and we'll start the class. Right. So, in the previous session, we understood the different types of activation functions that we generally use in neural networks. Before that, we'll quickly revise the earlier concepts as well. What is a neural network? We have understood the overview of deep learning. Then we understood the variants, artificial intelligence, machine learning, deep learning, and its types. Okay. So the differences between these three, uh, and then we started with the basic neural network architecture, how a neural network works, what are the layers that we have under neural network. We have discussed. Yes. So in a neural network, in general, you have three different layers: input layer, hidden layer, and output layer. So the inputs will be passed from the input layer. Okay, it will be passed from the input layer, and we have two important parameters within a neural network, and they are called weight and bias. So these weights and bias initially they get randomly assigned. They are randomly assigned between each and every connection between two neurons. Okay, wherever there is a connection between two neurons, okay, between the neurons of two different layers, so there will be a weight and bias assigned. So, what is the purpose of weight? If you ask what is the purpose of weight, that is the question that we'll have. Anyways, we have understood the concept of weights in the previous session. We quickly, understand once again. So, the inputs that we have will be passed into the neurons in the input layer, and these values will be multiplied with the weights so that we'll get a output, and this output will be you know transformed between each and every layer in the neural network. And to this output we'll also add a bias to ensure that the activation function to be moved towards the left side or right side. So at the initial stage, the weights and the bias they get randomly assigned, and this is because of the uniform distribution or normal distribution Z. So Gaussian distribution will be used, or Savior initialization will be used to initialize weights and bias, random numbers. Then within hidden layer and output layer neurons, you will have two components. The neurons present in hidden layer and output layer will have two components within each and every neuron, in which the first part is nothing but summation function, and the second part will have activation function. What is the purpose of summation function? Summation function will calculate the weighted sum. The weighted sum will be calculated. Okay, it uses the formula summation of wi multiplied by xi plus v. Okay, where I takes the value from 1 till n. So depending on number of connections that particular neuron has, the weights and the input values will be multiplied to this, product. The bias gets added, and this will be the output for the next part, that is activation function. Activation function will ensure whether that particular neuron has to be fired or it has to be misfired. So within hidden layer and output layer, we'll use activation functions. So friends, if you haven't gone through my previous session, which we have discussed on activation functions and its types, just go through it, because today we are going to understand an optimization algorithm. It is gradient descent. Okay. So what is gradient descent and what are the variants? Okay. So we are going to understand in today's class. But anyhow, I want to quickly recap the activation functions as well. So let me go through it. We have discussed the components, and this is how the weights and bias. Once after the weights and bias get initialized, you know, uh, the activation functions will be used to transform the data from one layer to the other. And it also helps us to understand or recognize the hidden patterns. The complex patterns that particular data has will be understood by the hidden layers because of these activation functions. So what happens exactly? Once after getting the output, the loss gets calculated, and this loss is responsible, the main aim of a neural network is to minimize the loss. So how is loss calculated? Loss is calculated using y minus y hat. What is y? Y is nothing but your actual output, and y hat is your predicted value, right? So the difference between y and y hat will give you your loss. So this loss has to be very small. When you'll have the loss function small, a very small value, or when you'll have it to 0, when both actual and predicted value, if they are same, then obviously the loss function will be 0. So our main aim is to minimize the loss, right? So how is this loss minimized? The loss is minimized using optimization algorithms. An optimizer will be used in which the neural network starts back propagating. So friends, each and every topic, as I have discussed earlier, each and every topic we are going to understand, but it takes a time, a bit amount of time will be taken because you cannot understand all the topics in a single day. Probably you have to convince yourself and adjust accordingly. An optimizer algorithm like gradient descent. Today we are going to understand how gradient descent is going to work. So generally this gradient descent is widely used, and also the variants of the types of gradient descent algorithm. So what is the purpose of an optimizer? The purpose of optimization algorithms is, to bring this loss to a minimal value. But how? By back propagation. When the model starts back propagating, when the neural network starts back propagating, the weights which are randomly assigned initially, they get updated. They get updated using this formula. What is the formula? What is the formula, friends? Don't sit idle. Okay. Answer my questions in the chat. The formula that is used is new weight is equals to old weight minus eta multiplied by derivative of loss divided by derivative of old weight. So what you are doing? I'm going to take the old weights. Okay. So using the old weights, I'm going to subtract old weight from a component. Okay. And that component is nothing but neta multiplied by a gradient. This is called gradient, friends. Okay. Derivative of partial derivative of loss divided by partial derivative of old weight. Okay. And what is this eta called? Learning rate. What is this eta called? Learning rate. We'll talk about eta in today's class. Okay. So once the product got calculated, we are going to remove it from the old weight and we'll get the new weight. In the same way, we are also going to calculate bias as well. So weights and bias that are randomly initialized, they get updated in the back propagation. Why? To minimize the loss. This is what we have discussed, right? Yes. Then we started understanding activation functions. The main purpose of using activation functions is they introduce nonlinearity. Okay, as the data in the real world is nonlinear. Okay, they're not linear, friends. The data is nonlinear. So that is the reason we use activation functions to bring nonlinearity. Because of adding this nonlinearity into the neural network, it starts understanding the complex patterns and the relations in the data. Okay, and it is also helpful to determine whether a neuron has to be fired or not. whether it should be activated or not will depend on the activation function that we are going to use. So these are the primary advantages of adding activation functions in a neural network. And without an activation functions, a neural network is similar to your linear regression. So again, friends, if you don't have any knowledge on linear regression, how linear regression works or what is linear regression, just go through my previous session that I have discussed on linear regression as well. Okay, because here you'll have a linear relation between your y and x, input and output. But if you don't have activation functions in neural network, the network that you're trying to build is similar to a linear regression model. So what is the use? There is no use, right? So because of activation function, we are going to decide whether a neuron has to be activated or not. And moreover, this particular activation functions bring non-linearity into the model. Then we also started understanding the types. Types were also discussed. The first type is sigmoid function. So sigmoid function, the formula is given here. F of x is equals to 1 by 1 plus e power minus x. And where is sigmoid activation function generally used? Sigmoid activation function is used in output layer neurons. Why? Because if you are working on a binary class classification problem, if you're working on a classification problem in which there are only two classes, we generally use sigmoid activation function in the output layer neuron. The main reason is the output of sigmoid activation function will be between only 0 to 1. The range is between only 0 to 1. So if the values are greater than 0.5, the threshold is taken as 0.5. So if it is greater than 0.5, yes, obviously the value is 1. And if it is equals to or less than 0.5, the value is 0. So it helps us to classify into two classes, either pass or fail, whether a person will take a loan or not. So in these cases, especially in binary classification tasks, we use sigmoid function in output layer neuron. And what are the challenges that we observe in sigmoid function? Why can't we take a sigmoid activation function in hidden layer? Because we have some limitations with respect to sigmoid activation function. And that is vanishing gradient. The first one is vanishing gradient. What is this vanishing gradient? Probably, today's class will understand it. Yesterday, anyhow, I have understood, I kept it clear. But anyhow, I'm going to repeat one more time. Vanishing gradient is nothing but when you try to take the derivative of, the gradient. So for example, if I use sigmoid activation function in my hidden layer, so what happens when we update the weights? It uses this formula. New weight is calculated using old weight minus eta multiplied by derivative of loss divided by derivative of old weight. Right? So when you try to update your weights, this gradient has to be calculated. What is this gradient? This gradient is given as derivative of your loss function, partial derivative of your loss function divided by partial derivative of your old weight. So whenever you try to take the derivative of sigmoid function will lie between only 0 to 0.25. This is actually proved. Okay, it was experimented and also proved that the range of derivative of sigmoid function will lie only between 0 to 0.25. So when the values are, if they are becoming, if the gradient values, if they are becoming very, low, if they are very small, what happens? It use chain rule and the values will be very small so that your old weight will be approximately same as your new weight. So that means the gradient that you are trying to calculate, this gets vanished. Why? Because I'm going to get a very small value Again, to this small value, I'm going to multiply eta, which is again a small value. What is the purpose of eta? Eta is nothing but learning rate. Eta is nothing but learning rate. So this learning rate, in general, can I take a big value? What is the purpose of learning rate is, I'll talk about learning rate first. Whenever you are using learning rate, this helps us to converge. Okay, so for convergence, we use learning rate, friends. So how fast the model has to converge? The learning should be very fast or should it be very slow? That will be decided by the learning rate factor. It's a hyperparameter that we use in this process. Okay, so if you are taking very large value for the learning rate, the model jumps from here and there. Okay, I'll show it as part of gradient descent, but the convergence will be very fast. It never tries to reach local minima as part of gradient descent algorithm. What if you take a very small value for learning rate? The convergence across the process will be very slow. So you'll take an optimistic value. Okay, you'll take a best value so that obviously it will be a small. It will not be big. It will not again be a very small value. So you're going to take a value and that value will be multiplied with a small value. Again, the output will be very small value. So whenever you're trying to remove a very small value from one particular value, the output will be same. See, if I have world weight as 1, okay, and if I remove 0.0001 or 0.001, that is the output of my learning rate and the gradient. So what the value is, I'm going to get 0.0, no, then 99. Sorry, this is also 9. My bad. So is this close to 1? Yes. So obviously your new weight will be close to old weight. Okay. So there will not be any change. This is called as vanishing gradient problem. The gradient that you're trying to calculate gets vanished. Okay. So because of this, we cannot use sigmoid activation function in our hidden layers. And moreover, it is not zero centered. It is centered at 0.5, the threshold, the default threshold. Okay, because of this again, the convergence will be slow, friends. Okay, this might cause the weight updates to slower convergence. So these are the issues which stops using sigmoid activation function in hidden layers. And later on, we discussed the tan H activation function where the zero-centered problem was being overcome. Okay, because tan H activation function uses the formula e power x minus e power minus x divided by e power x plus e power of minus x. Since I'm using exponential, the limitation will be, computationally expensive. But the vanishing gradient problem is still there. Why? Even though if you try to take gradient for this formula, you'll get the values between 0 to 1. Okay. So since the values are close to small values, again, the vanishing gradient problem still exists in tan H function as well. Right. So for this, we have introduced a function called ReLU. Rectified linear unit has been introduced. What is the purpose of ReLU activation function is it overcomes both gradient descent, vanishing gradient descent, gradient problem that was encountered in both sigmoid and tan H functions, as well as it is zero-centered as well. Right? So the activation function ReLU can be used in hidden layer neurons as an activation function. Right? So for that reason, we started using ReLU and its variants in hidden layer neurons as an activation function. What is the formula that is used for ReLU activation function? ReLU activation function uses, 1 minute. Yes. max of 0 comma x. So it is very simple. If the x value, if the z value, if it is greater than 0, the output will be x. If it is less than 0, it returns 0. What is the challenge that you observe here in ReLU? In ReLU, we have the problem is dying neuron. Because for suppose the values are less than 0, assume. What happens if I use ReLU? That ReLU activation function will return me 0. So because of 0, what happens? That particular neuron gets died. It dies. Okay. And because of this, it stops learning. There is no learning happening. So no more because it got dead. And this particular dying ReLU issue was fixed by leaky ReLU function because it uses the same formula, but there is a slight difference between ReLU and leaky ReLU, where we use 0.1 into x comma x. So instead of keeping the function as max of 0 comma x, we keep it as max of 0.1 into x comma x. Right? So leaky ReLU function is used to overcome the issue of ReLU activation function. But is it computationally expensive? No. No, it is not computationally expensive. Right. And the problem that you see here is it is not zero-centered. Okay. So then we understood exponential linear unit as well, ELU. So which is a variant of ReLU itself. And we use it for the same hidden layer neurons as an activation function. But the challenge that you see here is it is computationally expensive. The reason is it uses exponential in its formula. Because of it, we say it as computationally expensive. Then we also discussed the softmax activation function. The softmax activation function uses the formula as e power zi divided by summation of I equals to 1 till n exponential e power zi. So the range is between 0 to 1. But this softmax activation function is used for what is the purpose of softmax activation function? It is used as an activation function for multi-class, uh, you know, task. If you are working on multi-classification, okay, you can use softmax activation function as a activation function in output layer. This helps us to predict the probabilities for each and every class. Accordingly, wherever for which class, if you have more higher probability, that will be written as output. So since it is using exponential, the first limitation for softmax is computational expensive, and moreover, it is sensitive to outliers. So outliers should not be present. If you have outliers, the results will not be good. All right. So this is what we have understood as part of the previous session. And in today's session, we'll understand loss function and cost function. So friends, have you ever heard these terminologies across machine learning and deep learning algorithms? All right. So every one of us, working in this field of AI, okay, ML, DL, we will be, hearing the words loss function, cost function. What is loss function and what is cost function? Loss function is nothing but, you know, we are going to measure the error for a sample. See, for a single training example, if you calculate the error, it becomes loss function. And it is given by actual minus predicted. The difference between your actual minus the predicted value per single instance. For if you are taking 100 rows and if you're trying to build a neural network on it, if you're training under a neural network process, okay, each and every row, when you are going to pass the inputs for each and every row, you'll get error. Yes. So that error is named as loss function. Okay, that error is named as loss function. For each and every instance, you get error and it is named as loss. Then what is cost? cost is nothing but the average of loss. So if you have 100 records, you'll get 100 loss functions calculated, but only one cost function. Cost function is nothing but the average of your loss functions. Okay. So whatever error you are representing for the entire data set, it is nothing but the entire, for the entire data set, whatever you are trying to represent, it is a cost function calculated. And let us discuss this cost function and loss function for a different, uh, probably for different cases. Let me take regression first. If you take regression problems, the first one is the loss function that we have is mean squared error. This becomes our cost function, but loss function is actual minus predicted. Okay, so we may get a negative value. Because of that, I'm going to square the value. Okay, and I'll calculate the average of all these values of all the loss so that I'll get mean squared error, which is nothing but cost function. I hope it's making sense. So the error that you're trying to calculate is a loss function, and mean squared error for a regression problem will be a cost function. In the same way, instead of squaring, I can also go and take absolute error. Yes. So when I'm trying to get the difference between actual and predicted, I may get a negative value. Because of that, I'm trying to square it. Square the error. Error cannot be negative. So instead of squaring, I can also go with modulus, which returns me the same value. Yes. So I'm going to take modulus, and mean absolute error will be a cost function for regression problems. Both mean squared error and mean absolute error are two cost functions that can be used. Then what about classification problems? For classification problems, we use, again, under classification problems, we have two types, binary class, multi-class. So for binary class, we use binary cross entropy. So this will be the loss function that is calculated for a binary classification task. Okay, it is binary cross entropy. And here is the formula. You need not memorize the formula and all, not required. In the same way, if you are working on a multi-class classification problem, the cost function that will be used is categorical cross entropy. So for binary problem, it is binary cross entropy. And for multi-class, it will be categorical cross entropy. So these are some important points that should be learned as part of, these loss and cost functions, right? Now let us go into the topic of gradient descent. What is this gradient descent? And let us also understand what are the variants that we have as part of gradient descent, right? So probably I'll explain you from here. Gradient descent is an optimizer, friends. You see here, gradient descent is an optimization algorithm which helps us to minimize the loss function. The loss that is getting calculated at the end of forward propagation, it should be very small, right? So the main aim of optimization algorithms is to minimize the loss function. Initially, as the weights and bias are randomly generated, the loss function that is calculated might be not that much small. So using optimization algorithms like gradient descent, we are going to minimize the loss function. Okay. So it helps us to, adjust the learning rate, and it also helps us to, handle the issues like vanishing gradient problems and speed up the convergence. So we'll discuss what is gradient descent. You see, so when you take cost or loss function on x-axis, and if you take weights on x-axis, and cost and loss function on y-axis, this is how, we'll have the distribution. Initially, if your cost or loss function is here, let me do one thing. Probably, yes. Initially, you may have, your loss or cost function, which is calculated at high position. At high position, okay? So, your loss being very high, your loss, whatever you're trying to calculate, which is very high, this has to be, brought somewhere to here. This is called as local minima. This is called as local minima. What is this local minima? Local minima is nothing but, you see across this plot, where do you see the smallest loss? Where do we have the minimum loss? Exactly here? Yes. So this is the point where we observe the smallest or the least value for our loss function, and this has to be obtained using an optimizer. And today we are going to discuss gradient descent, one of the important and the basic fundamental optimization algorithm, which helps us to minimize our loss function. But how can we bring the loss function, which is very high at the initial stage, to a very small value that is at the local minima, is using any of the optimizer. And in today's session, we are going to learn gradient descent and its types. So friends, focus. So as the model, okay, now you have understood the purpose of learning gradient descent. This gradient descent, being an optimizer, it starts as part of back propagation. When the neural network back propagates, what happens? Your weights, bias get updated. Yes, they are recalculated actually. Yes. How? Using that formula. Old weight is equals to new weight minus learning rate multiplied by derivative of loss divided by derivative of old weight. Yes, exactly. But, you know, in the backend, it uses an algorithm. It is nothing but gradient descent. So these weights and bias, they are updated using an optimization algorithm. Okay. And here we are going to use gradient descent, and using gradient descent, we are going to update weights and bias. So if you see here, if I take any one of the point on, I'll make this graph into two parts. Probably I'll cut exactly at the local minima part. So I'll have left hand side and right hand side part. If you see here, if my initial weight, if it is very small, which are randomly assigned, if they are very small, my loss is very high. That's what we can interpret. So this is loss and these are weights. Your weight is very small at the initial stage. What should happen? What happens to your loss? Your loss is very high. So if you take the left hand side part, your loss, which is very high, has to be bought somewhere here. But how can we achieve it? Your weight should be coming exactly, it should increase. So that can be done using an optimization algorithm. Okay. So within the formula, if you remember, oh, sorry, it's new, right? New weight is calculated with old minus learning rate multiplied by partial derivative of loss divided by partial derivative of old weight. Partial derivative of old weight. So what happens if my weight is initially here? So if I take, so friends, can you explain what does this mean? This is represent gradient, right? What exactly you mean by dou y by dou x or dy by dx? If I strictly speak about derivatives, what do you mean by dy by dx? Dy by dx is nothing but, the rate of change in y, okay, with respect to x. In the same way, if I am going to change the old weight, I am going to calculate, you know, the rate of change with respect to the loss. What is the change in loss? Okay, with respect to the change in my old weight. That is what we are going to calculate. If you take any left-hand side part, okay, any point on this particular curve, okay, exactly if I take here, and if I draw a tangent, which exactly meets at one point, okay, observe the downward point. Okay, so to the right hand part of this line, observe the right hand part. Where is that arrow mark pointing? If it is pointing towards downside, we say the gradient that we are going to calculate will be negative. So here the slope is negative. So if the gradient is negative, negative multiplied by negative will be a positive value. So the new weight that we are going to get will be added. The old weight will be added with some value. So obviously your new weight keeps on increasing. So from here it goes here, then so on. So this is called convergence, friends. This is called convergence. And if you take any part on the right hand side of the curve, probably if I take here, okay, and if I draw a tangent, okay, which exactly meets at one part of the curve, observe the right hand side part of that point of the line. Take the right hand side part. This is left hand side and this is right hand side. Where is the arrow mark pointing? It is pointing towards right hand side. I mean to the top. So obviously the slope will be positive. If the slope is positive, you know, positive multiplied with negative, the output is negative from the old weight. Okay, if your old weight is around here, okay, from the old weight, what you are going to do? You are going to remove some value. So obviously the weight gets reduced to here, then here. So here, so this is called convergence. Okay, so this convergence will depend on the value of eta. How fast the convergence should be done will be depending on eta. Okay, I have discussed, right? If you take a very big value, probably you may not experience this. If you take a very big value for eta, your convergence in the algorithm might be like this. And probably it never reaches to the local minima. So because of this, you cannot minimize the loss anyhow. That is what we have discussed. If this eta is a very important hyperparameter, okay, if you take very big values, this particular weights, they never reach to the local minima value. The point that you see here will never return to the local minima value. And because of that, you cannot get the loss function, the minimal loss function calculated. What if you take very small value? Actually, instead of taking a big value, I'll take small value. If you take very small value, the convergence will be very small, very small. So it takes a lot of time to reach this local minimum. So instead of taking very small value or very big value, we have to take best value for eta, and that can be experimented when we go and do a use case probably in our next session, right? So this is how gradient descent works. Okay, now you might have understood, right? How the weights getting updated. This is because of an optimization algorithm and widely used. The basic optimizer is gradient descent, right? So now let us go and understand the variants under gradient descent algorithm. Gradient descent algorithm have three different variants. One is batch gradient, stochastic gradient, and the third one is mini batch stochastic gradient. So what are these? We'll understand. The first one, batch gradient descent. Batch gradient descent, it computes the gradient using the entire data set. For each and every iteration, the entire data set will be used. So that means if I have 1,000 observations in my data, the entire data will be used, to compute that gradient. Again, what is iteration? We'll understand, friends, no issues. Okay. Then I'll explain all the types of variants using an example, no worries. Let me go and talk about stochastic gradient descent. Stochastic gradient descent, it computes the gradient using each and every instance. So if you have 100 records in your training data, you know, each and every instance, that means each and every row will be used to compute the gradient. And it takes lot of time. Okay, the parameters get updated for each and every uh, you know iteration. So no, hold on, no worries. What is iteration? What is no epoch? We'll understand once after understand mini batch gradient descent. Then the third variant is mini batch gradient descent, which is computing the gradient based on a small subset of the original data. So if you have again the same 100 records, I'll take a subset. Okay, so probably if I take 10 at a time, so in this way I'll have only 10 records for each and every iteration. Okay, so I'll take each and every 10 records and I'll pass it as a subset to calculate my gradient. But probably Akhil did not understand the variants. Whatever you have discussed with respect to gradient descent, sorry, the variants like batch, then stochastic and mini batch. Okay, we have batch, mini batch, and stochastic gradient descent. But in order to understand these, let us go and understand what is iteration and what is epoch. So this is very important, friends. Okay, you are supposed to understand the difference between iteration and epoch. Then we'll understand batch, stochastic, and mini batch gradient descent using an example of iteration and epoch. For this, I'm coming with a Word file because I have kept an example as well. Right. First one, let us understand iteration. What is iteration? Iteration represents, updating the parameters. What does the parameters represent? It represents weights and bias. So if you are updating weight, the parameters of your model, okay. So using a batch of data, it might be a single instance or a batch or the entire data set. We are not focusing on it. If you are updating the model parameters, weights and bias, it is called as iteration. It is called as iteration. When these get updated in the backward propagation, as part of backward propagation, we update model parameters like weight and bias, right? So for example, if you have 1,000 training samples, nothing but 1,000 records, and if my batch size is 100, so that means in each and every batch, I want to pass 100 records. So how many batches will I get? 10. Simple. 1,000 divided by 100. So obviously I'll get 10 batches. So within these 10 batches, I'm going to pass my data. One batch at a time, one batch at a time. So first initially batch 1, then batch 2, then batch 3, so on. Okay. So how are iterations calculated? Whenever the first batch goes, what happens? I'll pass batch 1. As part of forward propagation, it calculates loss, right? Once after calculating loss, what happens? The model has to back propagate? Yes. Within the back propagation, the weights and the bias get updated. So if it is getting updated, it is an iteration. So one batch, you are getting one iteration. So 10 batches, you are going to get 10 iterations. So number of iterations will be calculated by total training samples divided by batch size. So 1,000 divided by 100, So that means we have 10 iterations. Now let us discuss what is epoch. Let us discuss what is epoch. Epoch is nothing but, you know, epoch is nothing but you are completing the entire data. Okay. If we are completing forward and backward propagation through the neural network once, it is named as epoch. So in simple, forward propagation plus backward propagation is epoch. Is epoch. So why you should go with multiple epochs? Because if you pass your data only for one epoch, okay, if you are taking only one epoch, obviously that means your entire data, which is being, you know, forward propagated and backward propagated, okay, where the entire data is being undergoing the training, it just learns the basic part. It does not go and understand the complex patterns. Impossible, right? So because of this, we go and use multiple epochs so that the complex patterns will be understood. Okay, so one epoch is nothing but completing the entire training data set. Whatever the data that you have, if it is being passed forward and backward, okay, so all the records should be complete this. Then it is named as epoch. Right? Now let us understand the relation between epoch, iteration, and batch size first. Then we'll take the example. So you see what I'm trying to do? This is the formula for calculating iterations across the epochs, right? And total iterations is given as total iterations per epoch multiplied by total. Right. So here I'm going to take an example, friends. If there are 10,000 samples, that means 10,000 rows in my data set. And the batch size, if it is 500, okay. So what does that mean? That means in a whenever you're training your model as part of the neural network, you know, in a batch, we can send only 500 records max. Okay. So your 10,000 samples that you have will be converted into batches. How many batch you are going to get? It's nothing but 20. So probably 520s are 100. So 20 iterations will go. It takes 20 iterations because one epoch, I mean, in one batch, only 500 samples are being sent, right? So whenever a batch B1 has 500 rows, B2 has 500 rows. In this way, I should take B20, which also has 500 rows. If you add all these, you'll get the original data. Okay. When B1 passes, the model forward propagates and it backward propagates. So one iteration is observed. Then one iteration is observed for B2. So on till B20. So how many iterations you are going to get? 20 iterations. Per epoch, you'll get 20 iterations. But how many epochs in total? There are 20 epochs. So 20 epochs, in 20 epochs, obviously, for each epoch, it is 20, right? The number of iterations are 20. So for 20 epochs, 20 multiplied with 20, you'll get 400. So that makes the difference, right? I'll try to explain the differences directly. The definition for iteration is one update step using a batch, whatever the batch that you're going to use, batch size, one update with respect to the weights or the bias. No, the model parameters. If they get updated, it's a iteration. Epoch is nothing but one full pass of the entire data set. If you're passing the entire, see, if I pass all these batches, that means I complete one epoch. Why? Batch is not passing the entire data. It is just passing a subset of data. Out of my entire data set, it is just passing only 500 records. So what exactly happens is this undergoes iterations, because whenever I pass each batch, I'll get the model parameters updated, weights and bias. But is it completing one epoch? No. One epoch means you're going to complete, you're going to pass all the batches. That means you're going to pass the entire data set, which is an epoch, right? So that makes the difference between epoch and iteration very important. Now let me take an example for that variance of gradient descent. See, I'll take the variance of gradient descent, mini batch, batch, and stochastic gradient descent. And I'll take an example. For this, I'm taking the same amount of rows, 10,000 samples. What does batch gradient descent says? Batch gradient says, pass the entire batch in a single go. So all the 10,000 rows will be passed in a single go. But stochastic says each and every sample has to be passed. Mini batch says you're going to calculate the gradient by passing a subset of data. So this is what I have. The meaning for each and every variant of gradient descent. And the number of epochs that I want to pass is 10. Now let me calculate the iterations. So can you calculate the iterations for batch gradient descent, friends? And tell me what will be the value for batch gradient descent iterations. So how many epochs? First of all, 10. Whatever might be the algorithm, I'm going to fix the epochs to 10. And the batch gradient descent, okay. So how many epochs you are going to get? Obviously 10. Because I'm going to have, I'm going to pass the entire data set in a single go, right? So obviously 10 epochs. Yes. Now let me calculate iterations. When will be the, yes. Will it be 100? Just think of, because see, I'm just passing my entire data. Okay. So in one single go, I'll get both weights and bias get updated for one, epoch. Only one iteration is what observed. So obviously 1 multiplied by 10, you'll get only 10. It will not be 100. Why? Iteration is nothing but whenever the model gets trained, the parameters has to be updated. That is an iteration. Since I'm passing my entire data as part of batch gradient descent, I'm passing the entire data, right? So when I pass the 10,000 records, so obviously for each time, for each epoch, I have only once. The iterations per epoch will be calculated only once. So total iterations will be number of epochs multiplied by iterations per epoch. So 10 multiplied by 1 is 10. Making sense? Then let me take stochastic gradient descent. Stochastic gradient descent says, each sample has to be passed. It's not the entire data set, each and every sample. So obviously 10,000 samples we are going to pass. So that means iterations per epoch will be 10,000. Epoch says entire data should be passed. So entire data set is 10,000. How many iterations you are going to identify per epoch? It is 10,000. So total iterations will be 10,000 multiplied by 10. So it will be 1 lakh. Now let me talk about mini batch. Okay, when it comes to mini batch, it uses small batches to pass the data, to train the data. Okay, so what is the batch size that I'm going to take? 100. So iterations that I'm going to get per epoch will be 10,000. The overall data divided by number of batches will be 100. So per epoch, you'll get 100 iterations, but total iterations will be 1000, 10 multiplied by 100. So this is how we are going to get, you know, the output for different types of variants, that is gradient descent, iterations and epochs. The example is very simple. I took 10,000 records, okay, and I have fixed the epochs. Epoch is nothing but you are passing the complete data for once. I'm together talking about forward propagation and backward propagation. That is an epoch. But iterations are not that way. Whenever there is an update in weights and bias, it is an iteration. Okay. And the iterations will change in batch, stochastic, and mini batch gradient descent. Okay. So this is how we'll understand the differences between, you know, the variants of gradient descent algorithm. Taking the same data set, iterations, and the total iterations. Per epoch and total iterations is what you calculate. I hope it's making sense. And tomorrow we'll come up with a use case on artificial neural network where we'll take a project and we'll work on it. We'll implement whatever the concepts that we have learned so far. We'll implement on the data frames, right? So if you have any questions, feel free to ask. So if you don't have any questions, we are done for the day. And before you leave, we'll provide the feedback link, give your valuable feedback, and do share across your connections. As well as if you feel the session went well, hit on the like button. And if you have any questions, also post in the comment section. Okay, if you have any kind of questions, use the comment section to post your questions. We'll respond to your questions, friends. So the feedback link has been provided. Give your valuable feedback and suggestions. Right. So that's all for the day. Again, we'll meet in the next session. Until then, have a great day. Signing off. Bye. Take care.